By the time we get done with this video, we will have a complete redefinition of the trig functions apart from the SOHCAHTOA definition, and it should allow us to hop out a right triangle trig. So just really quickly, just to give you kind of an impetus for doing this video in the first place. Up until now, we've discussed right triangle trigonometry, where maybe we have some triangle ABC, and we can find, say, the sine, cosine, and the tangent of, say, some angle A, so long as we knew the side opposite, we know the side adjacent, and we know the side that is the hypotenuse, okay? So SOHCAHTOA would allow us to do this. What I want us to consider, though, is this. We only ever work with right triangles using SOHCAHTOA with the two acute angles, which means we're kind of restricted in terms of how big they can get. So it is the case that sometimes maybe I could find the sine of 89 degrees. It would be some triangle looks like this, where that angle right there is 89 degrees. Like, we could do it. But what if I wanted to find the sine of 90 degrees? Or say the sine of 180 degrees? How am I supposed to sketch a 180 degree angle, which by the way looks like this, and make a triangle out of that? So the whole kind of premise of this idea, or this video, is to get a way around this. Can we work around our SOHCAHTOA definition, or you work with it, in order to come up with a new way to evaluate trig functions of, say, any given angle? And that's what we want to do here. Okay, so we're still going to borrow from SOHCAHTOA, by the way. SOHCAHTOA, which, as you recall, means like the sine of, say, angle A up here would be opposite over hypotenuse. So we could say the cosine of A here would be the adjacent over the hypotenuse, and then the tangent, really quickly, just because we have to get them all down here, we say opposite over adjacent. So borrowing from this idea, we're going to head over here now to the left, and what we're going to do is we're going to say, now, instead of choosing some angle A that is in a right triangle, let's say this angle is now this letter theta, and let's let it be any angle, so long as it's in standard position, and we say let's let the point xy actually be on the terminal side of this angle. Okay, and so this is kind of the main thing that makes this work here. We actually have a point on the terminal side, but we say, look at this sketch here. This could kind of represent our situation. So we say, here's our x and y coordinate plane. We say, here's the origin, here's 0, 0, and we have some angle in standard position. But what I want us to notice is that point xy on the terminal side, yeah, that's this point right here. And the thing that's really important about this is we're going into this saying, well, I could use this definition so long as I know this. But the cool thing is, this angle in standard position, since it left the positive x-axis and rotated, in this case, in a positive direction and terminated in quadrant 1, since we have this point on its terminal side, we could literally say, well, since you left from the origin in the first place, that the bottom of this triangle, the bottom leg, is x. You know, that is the x value of this point. And we say, well, the height of this triangle is the y value of this point. So when you look at the x and y, you know, you could kind of look at it like this, x, y. And here's our triangle. We're saying that this is kind of the base, basey, and then this right here is kind of like the height of our triangle, okay? And we have some angle, recall theta here. Well, the nice thing about this is we could actually work SOHCAHTOA on this to go find the sine, cosine, and tangent of this angle theta just by knowing the x and the y of some point that just happened to be on the terminal side, which you know what, I'll tell you this, you're even going to know it in these problems, okay? So let's go ahead and illustrate real quick one more thing. We'll notice that this value right here, this is the letter r. Okay, and we use r to represent the hypotenuse length, but also r is the distance. Okay, I'm going to write this down. Is the distance from our point xy to the origin. Okay, and there are a few things we need to say about r. Starting with this, r is always positive. This is just the case, you guys. R is always positive. And also this, seeing as how we know some point on the terminal side xy, it seems to me that I would know the base of this triangle x and the height of this triangle y. If I wanted to determine r, what we could do is this, we could just use Pythagoras. So we could say if x squared plus y squared is equal to r squared, keeping in mind that we'll know x and y here, then we could say, then in general, we could say r equals the square root of x squared plus y squared, where, a couple things here. First of all I've done is taken the square root of both sides of this equation to get r by itself. So that's what you're seeing over here. And second of all, the thing I want to recognize is this, r is always positive, so we're going to put a big fat plus sign in front of this instead of plus or minus. And also this, these, we already know them. These came from the point. So our job is going to be terribly easy. All we need to do now is redefine the trig functions, okay? So basically, looking at this image up here, we say given any angle theta in standard position, so long as I know a point xy on the terminal side, and by the way, we can use those two to find r. So long as we know x, y, and r, we can find, say, the 6 trig ratios of this thusly. And we're going to define them this way. We say, okay, so the sine of theta. Now, when I go back up over here, we say SOHCAHTOA. Notice sine is opposite over hypotenuse, opposite over hypotenuse. So that would be like given angle A, is what I'm talking about, opposite over hypotenuse. When I look up in my image here, I see that my angle theta that I'm taking the sine of, I have an opposite side as y, and I have an hypotenuse is r. So in this instance, what we could say is this: given any angle theta, you notice I say any angle on the planet theta, so long as you know a point on the terminal side, x and y, you can always find its sine just by taking the y value of that point and dividing it by r. Where we said r, well, we could go find r. R is this thing right here. Okay, so moving on with our definitions, I want to get through these. We say, well, the cosine of this would be adjacent over hypotenuse. Well, here's our angle theta. We say adjacent side is this x value over this r value is our hypotenuse. So we say x over r. So we say x over r would be our cosine of this angle, any angle. We say, and the tangent of any angle in this case is going to be opposite over adjacent, where in this case we say opposite over adjacent is y over x. Okay, so the thing that is profound about this entire definition, this is a new definition. This is now no longer SOHCAHTOA. It says that you could give me any angle on the planet. It could be over 90 degrees. You could hop outside of a right triangle and still find, say, the sine, cosine, or tangent of something, so long as you just know a point on the terminal side, which is a really kind of a cool thing to say. So we're actually going to use this really quickly before we do. However, I do want to mention these, the reciprocal functions, and this is very important to know. Nobody memorizes the reciprocal functions. What they do is they know that they're reciprocals of the ones that they do memorize. So for instance, if I want cosecant and I want to, figure that out of my angle, I need to know sine first. I need to know y over r because it's going to be r over y. Recall that they're just reciprocal. So this will be r over x and this will be x over y. But these right here, mark this aside. We say this is our new definition of the trig functions. Well, that being said, let's go ahead and say we have an angle, and we'll say this is angle theta, and it terminates in Q1. We often see that there. And we'll go ahead and give it a point, the point 3, 4 on the terminal side. What we want to do is we want to use this new definition now to go eval all 6 trig functions or trig ratios of the angle theta. Okay, so here's the most important thing before we do anything here. When you do problems like this, you need to sketch it. And so we were told this. We said, well, we have some x and we have some y on the terminal side. So I'm going to go right 3 and I'm going to go up 4. I'm going to drop this point right here. We're going to label it. We say this is the point 3, 4. And the important thing to note here is this. This is some angle in standard position. So we say, really, here's our angle right there. That right there is the angle. I'm going to move this out of the way. Right there is our angle. So now we say, well, first of all, how can I make a right triangle out of this? Well, we could drop an altitude. And the nice thing about this is we already know this is 4. We already know this is 3. We knew this from these points over here, x and y. The only thing that we're currently lacking here is r. Now, for most people, we say, I know this is a Pythagorean triple, and I know that r is 5. But we need to find this, okay? So we say, well, how do I find r? Well, the definition of r is this right here. We say, well, if x squared plus y squared equals r squared, then r is always equal to this. And get used to filling in the formula. Basically, you're going to be filling in this guy, where these are the, remember, x and y values that we were given with this point. So I say x is 3. I'm going to plug that in. Y is 4. So we get this r equals the square root of 9 plus 16, which is the square root of 25, which is plus or minus 5. But remember, r is always positive. So we say r is 5. So when we want to find all 6 trig ratios now, we're just going to write them this way. You're going to notice that I just rip these out pretty quickly. We say sine theta, cosine theta, tangent theta. And they are ratios, so it's just some fraction here. And we're going to go back and we're just going to fill these in. We say, okay, well, using our new definition, and over here we say, all right, sine of an angle is the y value over the r value. So we say the y value at this point was 4. Okay, well, I'll put 4. And we say the r value is 5. We say so 4/5. And then we say cosine. Cosine theta is x over r. Well, the x value of this point right here is 3. And the r value right here is 5. I mean, we labeled this. And then we say, well, the tangent would be y over x. So I don't even need r on this one. I can just look at x and y. We say y over x. We would, in this case, get 4 is our y value, and 3 was our x value on our terminal side. And the cool thing is, it doesn't even matter which point you pick on the terminal side. This is always going to work for our triangle with similar triangles. So we say, now, the reciprocals, I don't even need to look at the picture. I can tell you the cosecant here. Let me go ahead and put that one there, and this one here, and this one here. But we say 4/5, so this would be 5/4 would be our cosecant value. And then we say secant is 3/5, so this is going to be 5/3, and that's our secant value. And then we say cotangent would have to be 3/4. Okay, so new definition of the trig ratios, but a profound one. So we're getting into negative values in our next video. Cheers.